Okay, it's on. Cool. All right, so what we want to do in this section is combine everything that we've done so far with respect to knowing the sine and cosine of very particular angles, knowing how to compute sine and cosine of angles that exceed the interval from 0 to 2 pi using symmetry and reference angles, and the properties of the circle so that we can generate graphs of the so-called sine and cosine functions, right? So as I have been mentioning throughout, we have to use radian measure because degrees are a circular measure and you want to be able to graph a function on the real line. And so we have to use the radian versions to do that. All right, so let's first consider the sine of the function f of x equals sine of x. Right? Keep in mind, if you think about your unit circle, as you trace a point going around the circle, the x-coordinate is always the cosine of the angle, and the y-coordinate is always the sine of the angle, right? So keep that in mind. That's what we're going to be using to generate our graph here. All right, so for one, we want to know what the domain, what values can you plug in for x and compute the sine? Well, we know you can always plug in any positive angle or any negative angle or 0, right? Because you can always go around that many degrees or radians around the circle in either direction, and you'll always have a point on the circle that corresponds to it. So the domain of sine is all reals. Okay? The range, however, is restricted, right? So the biggest the sine value is corresponds to the largest the y value ever gets on the unit circle, and we know that that value is 1, right? It occurs when the angle is pi over 2, because at pi over 2, the y-coordinate is 1. The lowest value that's attained is down there at -1, right? When theta is 3 pi over 2, the y value is -1. Every value in between there is attained just by rotating that terminal side from 1 down to -1. And so the range of this function is the closed interval from -1 to 1. All right, so now we have to use an analysis of the circle as the y-coordinate of the points change. So as the theta, as the angle changes from 0 to pi over 2, so it goes from, starts here, and it goes up to pi over 2, at 0, the y value is 0, right? Because the point is on the x-axis. At the point 1, 0, the y value is 0 there. Likewise, at pi over 2, the y value is 1. Okay? But as the theta goes from 0 to pi over 2, the y value changes gradually from 0 to 1. And so the graph rises, it's increasing from 0 to 1 as x goes from 0 to pi over 2. Okay? Once we're at pi over 2, as we go down to pi, in a very like manner in terms of speed, it goes from 1 down to 0, right? The y values we're looking at again. So the y value of the point at pi over 2 is 1, the y value of the point at pi is 0, and it decreases steadily from 1 down to 0. If you continue from pi to 3 pi over 2, right, that y value starts at 0 and ends at -1. It gradually, at the same speed, decreases towards -1. And then once you're at 3 pi over 2, as you go up to 2 pi, now the y values start to increase from -1 back up to 0, right? And so you get this shape that looks kind of like this, where it's literally a kind of a wave from 0 to 2 pi. All right, and then the question is, well, we went from 0 to 2 pi. What if I continue on from 2 pi going to 4 pi, let's say? Well, we know the function repeats, right? So the y value, once you're at 2 pi, that's the same as where you started from. So the exact same pattern is going to repeat from 2 pi to 4 pi, from 4 pi to 6 pi, so on and so forth. Exactly the same pattern, because you have the terminal sides correspond exactly to what they were in 0 to 2 pi. And then if you were to go from 0 clockwise, right, it's going to repeat the pattern, but now the order is changed, right, because you're going down into the 4th quadrant first. And so as you move to the left, it's just going to repeat where it started off, kind of that same pattern, but now extending to the left. So if you put all that together, my hand drawing in the arrow side, what you get is a graph on 0 to 2 pi that looks like this. That's the wave there. And then if you replicate it, like I was saying, on subsequent intervals, either to the right or to the left, you get this literal sine wave pattern. Okay? That's how you generate the sine function. The cosine function is basically the same exact analysis, but now we're not going to look at the y values, we're going to look at the x values. All right, and so domain and range are the same, right? There's no value you can't take the cosine of. And the range, well, you want to look at where the x coordinates can range from on the unit circle. Well, it can go all the way from -1 to 1, right? That's the biggest and the smallest the x values ever get. And so the range of this function, which are the x values of the points on the circle, they go from -1 to 1. All right. In terms of getting the graph of cosine, we start at the point when the point when the x is 0, that corresponds to the angle 0. That point, or not x is 0, the theta is equal to 0. And so the x value on the x-axis of that point is 1. As the angle goes from 0 to pi over 2, that point travels from that point to this point, but that means the x value changes from 1 to 0. Right? And then it's the same way, if I'm from pi over 2 to pi, the x value starts here at 0 and it goes gradually down to -1. Once I'm here, this point goes from that guy to the point of the negative y-axis where the x is 0. So the x value goes from -1 to 0, and then eventually from 0 back up to 1. Right, so you're getting the same sort of behavior, but not in the same order. Right, so it's kind of like the same exact wave, but it's been translated. Right, and so what you're going to get is a graph that looks like this. So it's like sine moved over a little bit. Right, and if you replicate it on intervals just like we did for sine, that's end up what you get in this case. All right, so that's how you generate these graphs using the unit circle. Okay, so now what happens if I take a sine or a cosine of a constant multiple of x? Right, so we looked at that in terms of solving equations where we equated these guys to particular values. Now we want to see what impact multiplying an x by has on the graph, right? And so if you think about this, if I were to multiply, let's say, the inside by 2, so I took the sine of 2x. As the x goes from 0 to 2 pi, so just think about x itself, not 2x. As x goes from 0 to 2 pi, the value of 2 times x goes from 0 to 4 pi, right? And so what the 2 is doing is speeding up how quickly the inputs occur, right? So when x goes from 0 to 2 pi, the whole input has gone around the circle twice. And so that in 0 to 2 pi, it's going to replicate the graph of the original sine twice. And so it's going to mush it, right? It's going to actually occur quicker. And so how often it repeats is going to increase. So its period is going to go down, right? Same with the cosine. So let's take a look at this. This is what I was just saying. So this dotted graph here is the graph of sine of x. If I looked at sine 2x, it's going to occur twice instead of once in that interval because the 2x is happening twice as quickly. Had I looked at 4x, I would have had 4 replications of that wave in 0 to 2 pi. Okay? And so what we say is the period is half of what it was before, since it was 2x. It's 2 pi divided by 2. Had it been 4x in here, I would have divided 2 pi by 4 because I'm getting that many. I want to see how, what length of interval would correspond to a complete wave, right? And all you have to do there is divide 2 pi by the coefficient here, okay? Same thing for cosine. All right, and so here, the property is that if I take sine of bx or cosine of bx, we'll assume b is positive, because if it weren't, I could pull the negative out here and just get rid of it there by the odd and even identities. The period of these graphs is 2 pi divided by b, okay? So if b is a larger number, like 4 or 8, the period shrinks, so you're going to compress the graph. If the b is like a half or a fourth, you're dividing by a half and a fourth, so you're flipping it over, the period is going to increase, which means you're going to take the original graph and you're going to stretch it. It takes it longer for those inputs to generate a full period for the sine or the cosine, right? And that's illustrated up here, okay, in these graphs here. Now, what if we multiplied by a number instead of put a number times x as the input, right? So here we're keeping the original sine of x and cosine of x, but now we're multiplying each of those by a real number, okay? Forget about multiplying by a negative for the moment, right? If I multiplied by a negative number, I'm going to flip it as well, right? So forget about that. Let's just assume that the a is positive. If I were to put in 2 or 1/2 as my a value, just compare these at the very standard points here at the pi over 2 multiples, just so you can actually see easily how the change is going to occur. We know that the sine value at these values here are 0, 1, 0, -1, and 0. If I multiplied the sine of x by 2, I'm literally just multiplying the output each time by 2. So I'm going to get 0, 2, 0, -2, and 0. Had I multiplied it by originally by a half, I'm doing the same thing. I'm multiplying these outputs by a half. And so what it seems to be doing is that this multiple on the outside affects the height of the wave, right? The amplitude, so to speak. So if I multiply by a number larger than 1, it's going to stretch it this way. If I multiply by a number less than 1, between 0 and 1 rather, it's going to mush it down. And you can see that in the graphs that I have here. The red one is the original sine. If I multiply by 2, I'm stretching it up. Multiply by a half, I'm compressing it. But I'm not changing the period, right? The period is still the same. It's still 0 to 2 pi here. The only way to change the period is to change the input, to multiply it by a constant in the input. So the number on the outside simply changes its amplitude. All right, and then here, we're not really talking about vertical translations. So here we're always just on the x-axis, right? And so it's the amplitude itself corresponds to the absolute value of that number, right? If you had shifted it up, what you would do is you take the minimum or the maximum minus the minimum and divide that by 2, right? That works here as well, but there's no need to do that because I haven't shifted it, right? All right. Good deal. All right, and then here I say if the a is negative, basically, then the amplitude is the absolute value of that a, right? All the negative would do is flip it over the x-axis. We know about that from our reflection results. So all you have to do there is take the absolute value of that number out in front, and that'll give you the amplitude. All right, so here I want you to try out, we'll do a couple of these. I'll actually talk you through a couple of these after you've tried them, but I want you to determine the period and the amplitude and the range of each of those and see what happens. Okay, so pause the video, try that, and then we'll talk about a couple here in a moment. All right, so let's look at, let's say sine 2 times the cosine of pi x. The period always comes from 2 pi divided by the coefficient of the x. So it always comes from this guy in here. So the period is simply 2 units. The amplitude is always the absolute value of the constant being multiplied by it. So I'll take the absolute value of 2 on the outside. That's just 2. I haven't shifted any of these up or down. In fact, we won't either, right? We know that adding a constant to a function moves it up or down vertically. And you'll encounter those periodically, no pun intended. But doing that, you'll probably use a calculator or technology to get the graph anyway. And so there's no great purpose of analyzing them by hand at this point. All right, so the range is going to go from the min to the max. Since the amplitude is 2, I know that the smallest value I'm going to get is -2 and the largest is 2. And so you get a closed interval from -2 to do in this case. Okay. And then let's look at, let's say, number 3, right? The other ones are similar. Just want to talk about a couple when they're slightly different. The period is always 2 pi divided by the coefficient of x. So 2 pi divided by 2/3 pi. That gives you 3 in this case if you simplify it. The absolute value is, or I'm sorry, the amplitude is the absolute value of negative pi, which is pi. And so the range, excuse me, 1 second. Sorry, the dogs again. Okay. So the range goes from the minimum to the max. Since the amplitude is pi, we know the min is negative pi and the max is pi. Okay, and these two are done similarly. All right, so give the homework problems a go. Basically similar to what we just did, and let me know how it goes. All right, bye.